we've seen earlier in the course. The unknown is up in the exponent on these things. And let's review a few basic rules of using exponents before we actually start talking about these exponential functions. So, here's a classic example I've been using for many years. 2 to the 3 power, what does that mean? If you were trying to help somebody in beginning algebra and they didn't understand what 2 to the 3 power meant, how would you explain that to them? 2 times 2 times 2. It's repeated multiplication. 2 times 2 times 2. Okay? Now, compare that. So keep in mind, exponentiation can be thought of if you have a whole number exponent. You can think of that as repeated multiplication. This is nothing more than shorthand. Now, let me do something even more basic with you for just a second. What if I said 3 times 2? How would you explain that to somebody that's back in arithmetic? 2 plus 2 plus 2. You are adding 2 together 3 times. And that's where that word times came from. I taught for many years and not realized, it never dawned on me, why did we say 3 times 2? And it took me a long time for that to get into my brain. But that's what it means. So repeated addition is shorthanded, written as multiplication. Repeated addition. Repeated multiplication can be thought of as exponentiation. Okay? So if you understand what 2 to the 3 means, then when you see 2 to the 3 times 2 to the 4th, you're going to see that as a string of 2's multiplied together. How many of them? 7 of them. So that's 2 to the 7th. The darn textbooks always say if you have a fixed base, you add the exponents together. Well, here's an example. Here's an explanation as to why that is true. You understand it? It's 2 to the 7th. It's not 2 to the 12th. You don't change the base either. That does not become a 4. Okay? That should be very basic to you. It's a beginning algebra idea. And then here's another spot where people have trouble. In the context of what I mentioned here earlier, what does this mean with that 4 up there? That means you've got 2 cubed times itself 4 times, doesn't it? And then each of those are a string of 2's multiplied together, so you can see clearly that that's 2 to the 12th. Those little examples right there are the kinds of stuff where I see people make mistakes in college algebra when we're doing this as functions. Okay? Any questions? That should be very fundamental. Yes?
Don't you have to put 2 to the 4th too?
Where?
On the last one.
Hold it. What does this physically, if I say something to the 4th power, what does that mean? I'm covering up what I've got here. Doesn't that mean whatever is here, inside here, is multiplied by itself 4 times? There it is, right there. And each of those is a string of 2's. So there's 12 2's multiplied together there. The way you see it in a book is you see it says something raised to a power, and then you raise that to a power that you multiply these exponents together. Oftentimes it might be written this way. A to the m raised to the n power is equal to a to the m times n. That's the way you might see it in a book. Okay? Let's do a couple other basic things before we actually start talking about exponential functions. I did this, I think, a week or two ago with you, a few sessions ago, but let me just redo this. If I now build a exponential expression, let's make it simple. Let's say it's 3 to the x power. This is what I mean by an exponential expression. Something with a variable exponent and a constant base. a base, and you have a variable exponent up here. This actually is a function. And what I want to do, and I did this with you a while ago as I mentioned, is I want to build a little table of values. And why don't we start with a power of 4. So 3 to the 4th power is a string of 3's multiplied together, and that's going to be 9 times 9, which is 81. Okay, let's come down. 3 to the 3 power becomes 27. 3 to the 2 power becomes 9. 3 to the 1 power, let's see what it is. You look over here and look at this pattern. How you go from 81 to 27 is you divide by the base. To come down from 27 to get to 9, you divide by the base. To come down to understand, if you're teaching somebody in beginning algebra, what 3 to the 1 power means, it means 3 times, it's just 3 times 1, okay, in essence. Or you can explain it this way by looking at this pattern here. Divide 9 by 3, and you get 3. And then you can explain to a person what happens if the exponent becomes 0 by looking over here again, divide 3 by 3, and you see that you get 1. So no matter what your base is, no matter what the base is, a non-zero positive base could be any number bigger than 0, raised to the 0 power is always going to be 1. Always going to be 1. Then you can go on and explain what happens when you have a negative exponent. If you divide this result 1 by 3, you get 1 over 3. If the exponent is negative 2, it becomes, dividing by 3, isn't that the same as multiplying by 1/3, folks? If you ever divide something by 3, isn't that the same as multiplying the item by 1/3? So multiplying 1/3 by 1/3 is 1 over 3 squared. Now this pattern you see here, particularly with the negative exponents, leads you to an understanding of what happens when you see a negative exponent. So if I had something like 3 to the minus, say, 4 power, to try to explain 3 to the negative 4 power to somebody in beginning algebra, can you bring the image in a little bit? Because we've got a reflection on the board. Thanks. 3 to the negative 4 power, you're trying to explain this to someone, then what you could think of is you could say, oh, based on what I'm observing here, if I move this thing, think of it as over 1, fraction bar here, if I move it down under the fraction bar, it changes the sign of the exponent. Changes the sign of the exponent. So this becomes 1 over 3 to the positive 4. And then that makes sense to us because you know that 3 to the 4th is 81. So this becomes 1/81st. So the way I like to help people learn this stuff when you see a negative exponent is all you've got to do is if you ever cross that thing with a fraction, take it across the fraction bar, change the sign of the exponent. Let me show you why that works besides the pattern I showed you here. If I had 3 to the negative 4th, if I multiplied the numerator and denominator by 3 to the 4th, look what happens. Up on top, based on the story I told you earlier, what do you do to these exponents here? You add them together, don't you? Based on that little story I told you on the other board. You add those together and you get 3 to the 0. And down below, 1 times 3 to the 4th is 3 to the 4th. And so you end up with, we know now that 3 to the 0 is 1, so there you get your 1/81st. So this is the reason it works. And the easy way to remember it, if you ever cross the fraction bar with something, with an exponent, you just change the sign of the exponent. Practice this for a second. Let's say we had 5 to the 2x divided by 5 to the x. Notice that the bases are common. The bases are common, but we have variable exponents here. So what we could do to play with this is we could move one of these across the fraction bar and change the sign of the exponent. So if I took this thing down here and moved it up top, it becomes 5 to the negative x, doesn't it? And then what do we do with those exponents? We add the exponents based on my little story using base 2 as an example on the previous board. This is all intermediate or beginning algebra level stuff. But it's important that we review this so that when we start manipulating these new functions in a couple minutes, that you'll be comfortable with the basic fundamentals. So we add those exponents like Todd just mentioned. So 2x minus x is just x, 5 to the x. Okay, so this expression here of this fraction involving exponential expressions simplifies to that. Who's confused? Anybody asleep yet? That's good. Nobody's asleep. Okay. Yes, Jennifer.
Wouldn't it create confusion, though, to put a 5 times 5 next to each other like that?
No, that does not mean 5 times 5. It means this. See, this is not just a 5 hanging out here. This is 5 raised to the 2x power. So that's an item that is not separately just a 5 times that 5 over there. They're not thought of, and the base doesn't turn to 25. No. Okay, now it's going to take a little bit of review for some of you, but we'll have enough problems in your homework and so forth to be comfortable with this. Now, look at this. What would be another way of explaining, let's say I just wanted to look at 5 to the 2x for a second. Could we play with this based on that quick summary of basic rules I showed you earlier? That quick summary of basic rules I showed you earlier. Can we play with this? Notice these exponents are multiplied together. Everybody see that? Okay, 2 times x, right? And so that's the same as 5 to the 2 raised to the x, isn't it? Good, good. 5 to the 2 raised to the x. Now come back to the other board for just a second. Look right here. Camera. There we go. Okay. Look right here. 2 to the 3 raised to the 4th power is 2 to the 12th. Those exponents were multiplied together, 3 times 4. And we now come back to the other board. That's the same kind of stuff we see over here. 5 to the 2x becomes 5 to the 2 raised to the x. Those exponents are multiplied together. And so that you could rethink of this as 25 is your base raised to the x. Okay. So you could think of 5 to the 2x either as 5 to the 2x, or you could think of it as 25 to the x, just that portion of it. Okay, that should be enough to get us started now on actually looking at exponential functions. And I want to do something, instead of just doing a bunch of algebra with you, I want to try to make this real for you. I mentioned earlier in the course that exponential functions are probably one of the most practical things in mathematics that you'll ever encounter. Most practical and useful, particularly in finance and in science. In finance and in science. So, that was a review of some fundamentals. If we use this as our first example, y equals 3 raised to the x, and we have a table of values, there'll be a homework quiz.